This is a first talk in Coulomb branches known in seminar. In this semester, we will discuss the necessary preliminaries for Brewer-Mann-Finkelberg-Nakajima definition starting today. And then, the plan is to prepare for the definition, then discuss it, discuss basic properties, and maybe some examples of Coulomb branches. How are they isomorphic to like more classical objects in representation theory? I'm not recording. It's automatic. Cool. Okay, so today I will talk about equivariant, cohomology for reductive groups, and the plan for the talk is okay, we will see. So first, I will just discuss or remind definition of the principal bundles, classifying space, and characteristic classes. And main example will be Chern classes. So then I will define equivariant cohomology and discuss basic properties and examples. And finally, I will formulate the properties that are that hold for reductive groups. So homology for reductive groups. And discuss examples that will be relevant for the next talks. Okay, so let's start. Definition. Let me open. Okay, so first maybe a disclaimer. So so today we are doing topology. So all spaces that we consider are nice, like CW complexes, cell complexes, and even very nice. So they will all have cells only of even dimension. So to compute homology or cohomology, you just compute the number of cells of given dimension using compute homology, using cell homology, and all the differentials are 0 for degree reasons. Yeah, so no, like we will not do like some obscure topology today. So I'll do some topology and then it will end, and then we will do some algebraic geometry, and then we will do some horrible algebraic geometry. So that's the plan. Okay, so definition / reminder, principal, G bundle, over X is another space P with map to X, say P, and there is a cover of X. Okay, sorry, such that G X on P with the following property that there exists cover of X with open subsets such that inverse image preimage of UI is isomorphic to G times UI. So G acts on P, G acts on X trivially, map P is G equivariant or G invariant. So it sends all G orbits to the same point, and locally it's trivial. So locally, the preimage is just trivial G bundle, just group G acting on itself at each point. So this is the definition, and main example of such thing is that if okay, I guess I should stay here and please. So main definition of such thing is if G is GLN, then a principal GLN bundle is the same as vector bundle of rank n. And the way to see it is if you have a vector bundle E over X, then there is associated frame bundle so at each point you have Px equals to all possible bases in Ex with so and then E is union of Ex over all X and X, and you can topologize it using the fact that vector bundles are locally trivial. And you can go to the other direction. So like the reason is that the transition maps, both for such things and for vector bundles, are maps from intersection UI, intersect UJ to GLN. So in vector bundles, you describe change of basis. In G bundles, you just describe how does your trivialization differs. Any questions? Okay, so that was okay. Hopefully it all works. Yeah, and unlike vector bundles, G bundle is trivial if I don't leave it at the intersection. So you just use the section and action of G to provide an isomorphism between P and X cross G. And the only operation that we will need is pullback. So if there is a map, let's say F from Y to X, and we have G bundle P over X, then we have F upper star P, which is defined just as P over X times Y. So as using this Cartesian square, and it's easy to check that this is still something locally trivial. And we will need the following proposition that I will not prove, which is relatively standard, and where we actually using that our space are nice, is that if F, G from Y to X are homotopic, then the pullbacks are isomorphic. Any questions about that? Okay, so Zoom. That's what happens. Okay, looks good. And in particular, if X is contractible, then every G bundle is trivial. Just because pullback full point is trivial. Every bundle, bless you, every bundle over a point is trivial. Well, example, so we'll very quickly go to complex numbers, everything will be over C. So example, C n without 0 to P n minus 1 is principle, connection is principle C star bundle called tautological bundle. And it gives a linear bundle in a natural way called tautological linear bundle. Any questions? Okay, so yeah, we'll quickly go to less and less standard material. So now let's consider functor that sends space X to all principal G bundles on X. So set of isomorphism classes of principal G bundles on X. It turns out that this functor is representable in homotopy category of CW complexes. So there exists space called BG such that on X G is isomorphic to Gx, and this isomorphism can be made more explicit. So this BG comes with universal bundle, e.g. BG, it's G bundle, and e.g. is contractible. So if find such contractible space of action of G, free action of G, contractible space with free action of G, I can quotient to obtain such principal G bundle, and then any other principal bundle can be, so we can find map F of X to BG such that it fits into this diagram unique up to homotopy. Unique up to homotopy. Any questions about this definition? Okay, so ouch. No. Okay, so I see. Okay. No touching. So one of the examples of this is Rn, R infinity without 0 or C infinity without 0. So these spaces are contractible. It's if this infinity means that only finitely many components are non-zero. So this is like a direct sum, not a product. And this you can write explicitly homotopy between identity map and maps that sends everything to a point. Use that it's infinite, shift to the right, and then send everything to 1, 0, 0, 0, 0. So this is example of such, and they, by construction, have the action of R times or of C times. So this is E C cross, and this is E R cross, and the corresponding spaces are B. This is R is C P infinity, and the R star is C R infinity. Any questions? Too many letters. Other questions? Okay, so okay. So let me say some basic properties of this thing, and then I will kind of prove that this thing is indeed universal, or at least, yeah.
Why is it important that EG is contractible?
It comes. I mean, it doesn't like. It comes in a proof somewhere, but I don't know the proof, so it will not be important in the future. What will be important is that is universal property and examples for different groups. In particular, so I mean, naturally, V of for any two groups, V of G cross H is EG cross EH, just because you can cross everything. Cross this. I mean, it's just some explicit construction. If you have such space, then it works. So it's convenient that I can take these two spaces and say, okay, it's contractible as a product of contractibles, and G cross H acts on it freely. So, for example, this. Yeah, so we have this property, and also if H is a subgroup of G, then well, H acts on EG freely. So I can, one possible choice for H is EG over H. And so this allows you to, so if you know any algebraic group is a subgroup of GL and C, so if you know answer for this group, then you, if you found this space for GL and C, then you can use it just for any its closed subgroup. And answer for GL and C is as follows. G, L, M, C is all matrices n plus infinity, where we form definitely many non-zero entries of full rank n that have at least one non-zero line. These lines in C infinity are linearly independent. And naturally, if you quotient this by the group, you obtain the Riemannian of n of n spaces of n planes in C infinity. Any questions? Okay, so let me. Okay, why not? Let me prove that. Okay, not quite. So the. Let me prove at least one non-trivial statement that any line bundle on a space can be obtained from pulling back bundle on CP infinity. And yeah, also I didn't say, so we have like this G bundle, which was universal bundle. And here in both of these examples, the universal bundles are tautological. So for these cases, we have tautological universal bundle is tautological over each point representing a line is this line C or R. And notation is yeah, and then characteristic classes. Yeah, so let me actually prove it. So suppose that and I'll go from C star bundles to just line bundles. So C star bundles are the same as complex line bundles. Maybe I should have used real ones. Okay, let's hope it works. So we have X is union of UI, and assume that X is compact. Like this union is finite. It doesn't matter, it's just more convenient. Then over each, and we have this L over X. So L restricted to UI is isomorphic to UI cross C. So we define Fi of X comma Z, where X is in UI and Z is in C, as 0, comma Z, comma 0, Z in on the. ith place. So we choose ith open subset and send just this number to ith place. So this is something that, so Fi is a map from L restricted UI to C infinity without sorry, something happened. I guess not line bundle, just C star bundle. Okay, sorry, I guess I didn't check that. Yeah, so this is a non-zero number, which is good. Oh man. Okay. This should be good. So now let's consider partition of unity. So let alpha 1 alpha n be functions such that I guess maybe it's S. Sum of Si is 1 and support of Si belongs to Ui. Then we have function Si of x Fi xz, which goes from L restricted to Ui to C infinity. But we can, since support of Si belongs to Ui, which is zero, we can extend it by 0. So extend by 0 to continuous function, just from L to C infinity. I mean, it's a well-defined function. This one on Ui and 0 outside support of S, and they agree on the intersection. So it works fine. So there is a well-defined function, sum of Si Fi from L to C infinity, and actually C infinity without 0, since sum of S.
Oh, hi, Daniel. Maybe you forgot to move the.
Yeah, sorry, say it again.
Oh, maybe you forgot to move the camera.
Oh, yeah, sorry. Yes, I did. No, wrong. Yeah, perfect. Yeah, thank you. Yeah, so this is the proof of what happens, and yeah, so we just denoted by F, and then so we have. So let me maybe use one blackboard. So we have L x C infinity without 0, and this map is C star invariant. I should use R probably. No, I shouldn't. No, it's C star equivariant. So I can. So this is F. So I can find map G that fits. Just take a point, take any representative, send here, send back here. It does not depend on the representative because F is C star invariant. Because these Fi's are C star equivariant.
So I have a question.
Yes.
If you let Z be 0, then won't you get like the map?
Yeah, I decided it probably doesn't work, and
So
yeah.
that is in C star.
Yes. Sorry, yeah, Z in C star, and yeah, I think it works in this. Yeah, I hope it should. Yeah, so that's one example of how these things work, and topology essentially, well, at least topological proofs, partitions of unity and stuff, essentially end here. So, any questions? Okay, so the only thing I also finish or reminder. So okay, fact. Homology of Riemannian of n infinity is with coefficients, let's say is free polynomial ring in n variables in degrees 1, 2, n respectively. Yeah. If n is 1, it's just p infinity, and then in this case, the homology is just generated by one variable.
Degrees be even, maybe multiple by 2, or?
Yes, sorry. Yes. You are completely right.
Yes.
Yeah, everything over C. And we so if we have P over X, GLN bundle, we find the map F from X to good and infinity, unique up to a homotopy, and we say that ith Chern class of P is pre-image, pullback of EI, which belongs to 2ith cohomology of X. So this thing, so EI itself belongs to 2ith cohomology of Riemannian, and we pull it back to cohomology of X, and this is one of the possible definitions of Chern classes. There are more honest definitions, but we just use this algebraic formal definition. Any questions? Okay, yeah. I'll also use in the lecture. I mean, maybe I won't, but at least it's a good it's a good idea to see what happens next. So for like n equal 1, so h star of C infinity is C of C, and we can, I mean, we can also do it here. So, but here it's just easier to write. So T is first, I mean, by definition, first Chern class of all of -1. Recall that the universal bundle is tautological. So it's all of -1. So we use this as our universal bundle, and so its first Chern class is generator of cohomology ring. Any questions? Okay, so here we finish first part of our plan that I just erased. So now we turn to equivariant cohomology. So definition. Homotopy quotient of so now G space is a topological, I mean, nice topological space with action of continuous action of G. So of G space X. So we have group acting on a space, and to this pair. So first we define this quotient. So E G cross G X. So you take pair of points Px from product and say and quotient by relation Px is GP Gx. I think it should work. So quotient this product by a free action of G. So it's Gx free on this product just because it's X freely on EG. So it's essentially we don't want to consider just a factor. So X over G can be bad, or I mean it can be like bad as a topological space, or if you do algebraic geometry, it can lose too much information. So we change X to something that is homotopy equivalent to it, but with a free action of G. And if action is free, then you can quotient and nothing bad happens. You don't lose any information. So if action of G is not free, then this is something that remembers a lot, unlike just usual quotient X over G. And this can be like a non-separated topological space or something, so it's just bad. Okay, what should I do? Yeah, like this. Yes, and we use this construction to define equivariant cohomology, which is just so definition. If xg as are as before, then equivariant cohomology ring of X H star B of X is just homology ring of homotopy quotient. Yeah, that's the definition. Any questions? Okay, so let me do some basic examples. So like I've thought about this space. So let's assume that action of G is free. So if there is a free action, and in this case, X over G is a relative family. Is also a nice topological space. Then so there is always natural map from this homotopy quotient to X over G that just uses the second coordinate. But now we can actually consider it. It's an actual nice space, and if this is EG bundle, the fiber over point is EG. It's a sure, but then I get the whole EG. So it's a homotopy equivalence because EG is contractible spaces. homology, like roots. And so its homology ring is the same as homology ring of this vector. So in this case, we recovered just homology ring of a quotient. So this is indeed some kind of generalization, some kind of way to preserve information about this quotient in the case when the action is not free. Another example, so another extreme is that G does literally nothing. So if G acts on X linearly, then and this balanced product, we don't do anything to X, so it's just BG plus X, just quotient BG. And by tuner formula, we have H star G of X. So this is the homology of this product. So it stands a product of H star BG tensor H star of X. Everything is over C now. Everything is over C. So starting from this blackboard, H star is coefficient C. Integers or something. We can, but I guess I can. So just to fix something. Any questions about these two examples? Okay, so the one of the features is like with usual homology, you don't get anything from the point. Like it's just nothing. It's just field in degree 0 or Z in degree 0. But here, so let's just take in this example X equals to 1. Get trivial action. Here we just have BG, and we get H star G of what? H star BG, which is something non-trivial. It can be large. So as you see from this example, H C star equivariant homology of a point is just a polynomial ring in one variable of degree 2. So it's large. It's not just C, it's something else. Any questions? Okay, so let's discuss tori in more details. So let's our goal is reductive groups, and I mean essentially semi-simple group. So what we want is group, Borel, and torus, and like everything will be essentially torus. The torus will be our main thing, and well, we will kind of try to use it to obtain information about B or the group itself. Yeah, it's important to understand what happens with torus. And here. Like repeat a bit more generally. So let's say we so let's say we consider representation of C star of one-dimensional torus on C, which goes as D goes to Z to the A. And let's form the one of the nice ways to obtain the cohomology classes is to write some bundles and write the Chern classes. So we want to write something over EG, and it's already here, it's EG, but I can write a lot of line bundles over EG as follows. So I consider this representation, and I define LA as C cross sorry, let this be T so that I don't confuse myself. So C cross T E T. Let this be CA. So CA cross T E T LA. And this maps to E T and fiber over a point is C. So fiber this is ET to BT is T orbit, and it gets eaten into one complex line. So this is a line bundle over BT, and using this isomorphism, we have C1 of LA is AT. Because for A equals 1, you exactly get tautological bundle. So that's the reason we use O of -1 instead of O of 1 in this definition. So just to so that we don't have a flip of sign in this construction. Right, in line bundles as using representations of T. Yeah, and well, it's true because yeah, well, because you can compute it. Yeah, I'll describe properties of Chern classes later, but it's not hard to check that LA tensor LB is L A plus B, and C1 of L tensor N is C1L plus C1N. So it's something that can be proved using properties of Chern classes. Yeah, so this is okay, this may be that well motivated, but what we want, so we want to write that symmetric algebra of C star, the algebra with doubled degrees is isomorphic, naturally isomorphic to H star T of the point. So all this business is to write this isomorphism naturally. Using similar construction. So if you have integral character pi from T to T to C star, and you have a representation C pi where T acts by T. Like this fact is like easier to see but unmotivated. This one is harder to see but proved proved essentially in the same way. So T acts by chi of T, and we can see that we form L chi, which is C chi plus T T. I didn't talk about it, but if T is has dimension, we discuss product of groups. So if T is C cross N, product of N groups, then in T is product of several C lists. And well, in T is C infinity to the N. So using tuner formula, you can see that its homology is a polynomial ring in N variables, but you can also write it in the school way using this L chi. So we have this C1 L chi, and so this map I goes to C1 L chi is a group homology. Here is multiplication, and if you can also write here d chi goes to C1 I, which is now element of T star differential one. And yeah, now you can extend this map to an isomorphism of algebras. So use tensor product with C2. So this is only for integral elements. Then you can write non-integral elements just using linearity, and then you will extend here using multiplication. So if extends to an isomorphism from symmetric algebra star to ring of the T. It is equivalent motion of the point. Any questions? Okay, yeah, so that's what happens. And yeah, so another way to look at what happened that we will need, sorry, that we will, oh no, oh, you see, okay. Yeah, should work fine. So there is like a more general construction connected to that. Okay, so yeah, this was definition of equivariant homology and some basic examples and less basic but main example of a torus, of n-dimensional torus. Yeah, so now we do some more general constructions. So we need notion of equivariant vector bundle. So definition G equivariant vector bundle is a vector bundle in X where G acts both on E and on X. This map is G equivariant, and the action of G on E is linear in the sense that it preserves addition and multiplication by number. And yeah, maybe I should write an example that didn't is that if you have a tautological bundle O of -1, O, C, P, and then it is naturally C star -1, C star n equivariant, where C star n acts on C n without. I'm flipping here between like line bundles and C star. So this is construction for C star bundle, but it's. I mean, you can just add 0. So there is natural action of C star n on Cn, which computes with diagonal action of C star. So it provides both this action and action of C star n on C, P, n -1. And so this map is equivariant by definition. So it gives you equivariant C star bundle, which is the same as equivariant line bundle. Any questions about definition or example? Okay, yeah. So this is how it works. That's for CPN. You have both an actual action of torus, and you can lift it to a, or maybe better to say, an actual action of torus on space outside, and you can quotient to get action on CPN. And yeah, this. Also, yeah, example of such thing. And okay, so we want to write the homology classes as Choron classes of some bundles. Here, these are bundles on classifying spaces, BT, on something. But what if I want to be even lazier and not go to BT at all? If I want to work only with the space X. So this was what this definition was for. So I'll write equivariant Choron classes. So if I have a vector bundle X, G equivariant, let me maybe rename it V over X. Then there is a bundle over homotopy quotient. So I just multiply to ET cross G. So yeah, there is a map from this product cross G to this product cross G. And this is still a vector bundle of the same rank. And I define C I G, G equivalent Choron class I, Choron class of V. That's just Ci of this vector bundle, which lives in 2I cohomology of X homotopy quotient, which is by definition 2I equivariant cohomology of X.
What is T?
Sorry, everything is G here. Literally everything is G. The tea is too hot and I don't have enough water. Yeah, so this is the construction of these classes. And so now instead of considering bundles on the spaces, you can just write equivariant bundle on your space and consider it equivariant classes, and they will give you something in equivariant cohomology, and maybe they will generate it somehow in a nice way. Any questions? Okay, so I guess I will not prove this thing. So let me just show you. Yeah, let me show you right now what how can we use these things to describe a equivariant homology ring. So what I did not tell you is that each equivariant homology ring is naturally an algebra. I guess it like all so all our homology lives in even degrees. So like there is no greater commutativity, there is just commutativity. Everything is even. All cohomology rings are commutative. We discussed this cohomology ring of a point, and so that it's non-trivial. And actually, every cohomology is algebra over this ring for the following reason: just because you can send every space to a point G equivariantly with trivial action here, and there is a functoriality if you have first if you have f from x to y G equivariant, then you have pullback on equivariant homology, which comes just from multiplying f by EG, by this contractible space. So you have this pullback for equivariant maps. And so like, this is one example of equivariant map, just send everything to a point. And in this case, you have a map from this ring to equivariant homology of X, making it an algebra over this ring. Yeah, so like in nice examples, you have this ring, you write something else, like something finite, and you are done. So it's like since we'll discuss in a moment, but in nice cases, usual homology is finite dimensional, and this is kind of all what you have to find, just some finite dimensional number of classes. And let me at least describe equivariant homology of projective space. So let's take the same example of C star to the n acting on C P n minus 1. And just for like to compare, recall that usual homology ring of P n minus 1 is C of T over T to the n. So it lives in degree 0 to to n minus 2. But if we compute equivariant homology ring, so let's notation is so H star T to point is C of T1 comma Tn, just product of tensor product of cohomology ring for each C star, so polynomial ring in n variables, and in this case H star T of C P n minus 1 is C of T1 dot Tn zeta over product zeta plus ti I from 1 to n. So we have this polynomial of degree n with roots minus t1 dot 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 minus tn, and the only thing we have to do is to factor over the ideal generated by this polynomial. So there is a comparison that this is n-dimensional over C. This is free module of rank n over this ring, generated by 1 zeta dot 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 zeta to the n minus 1. Any questions? I think I'm not lying. Okay, I guess I don't have time to prove this, but like it's nice. You essentially have to prove that this is 0, and then you play with Chorn classes and sections of vector bundles. I have it in my notes that I will put somewhere in the website that will be created. Let's go to the third part, namely properties that are specific to reductive groups. Properties of reductive groups. Okay, well, the main thing is that if so we have G reductive, we have C cartan, we have W while, and the statement is that W. So for so if X is a G space, so if G acts on X, then C also acts on X naturally. So we can consider H star C of X, and it turns out that W acts on this ring, and its invariants are exactly G equivariant homology of X. And main, I mean, not main, but one of nice example of such thing is when X is just a point. So if X is a point, we have H star C point W H star G point. Well, we computed it. It's S of C star W, where this action is naturally its action of while group on a root space. Yeah, so this is this computes equivariant cohomology of a point, and so maybe even nicer example is G equal to GLN, where where in this case cohomology we discussed in the purpose of Chorn classes, of definition of Chorn classes, that H star of good and infinity, which is B GLN, is generated by generators of degree 2 dot 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 n to n. But this is also computes GLM equivariant cohomology of a point. And the statement is that this is actually H star of T, the point Sn invariance, while is Sn in this case. And what is this? This is C of T1 dot Tn. And similar, these are variables all of degree 2. And well, this is true. If you take a polynomial ring and take a semi-invariance, then elementary full or any, I mean, in this notation, these elementary polynomials in T1.Tn give you free generators of a ring of invariance. All these degrees. Any questions? Yeah. That's just symmetric. So the I is can be specified with I symmetric elementary symmetric polynomial in T1.Tn. And
But you have the fixed point by Sn also in the polynomial in the Ti.
yeah, fixed symmetric polynomials in T1.Tn, which are so I mean, as if maybe a fancier way to write it is that this is functions on TW invariant, which are functions on categorical function T. Yeah, that's how it works in this case. So yeah, maybe. I'll tell you what will happen is what I've saw happening in discussions around the school branches, that you have these 10 tricks with equivariant cohomology, then you forget what it is, all the definitions, and just use one of these 10 tricks at each step of your computations. So like this is trick 1, and trick 2 will be much smaller than trick 1, but still something useful. So I will not tell you about the main thing because I don't know, it will be later, or we will not use it in the seminar for some reason. Yeah, so just a bunch of tricks, examples and stuff. So second thing is that H star G prime H. So G over H. So I take G quotient over H on the right, there is still left action. I can ask about equivariant cohomology, and I just use definition. So this is to take a multiple quotient. G is G, so it's start of G over H. And this is a possible candidate for BH. I mean, all the classifying spaces are naturally homotopy equivalent by a unique homotopy equivalence by some basic Lemon category theory about representable functors. Unit by unit element. So it doesn't matter which one we choose. So this is BH. So this is H star of BH. Which is H equivalent H cohomology of a point. So I mean, it kind of it kind of nice. So asking about you intuitively want to quotient by G, and it works intuitively that G over H is point over H. So here is point, here is inch. So it's nice to make sense that you can take out some of the groups. Yes, so another important fact. So I've told how to compute G equivariant homology from T. Now let's talk about B. General statement is that H inside G is homotopy equivalent. Let's say information reject homotopy equivalent something. I hope it's the same. So then G equivalent homology is the same as H equivalent homology. And main thing for us is that B equivalent homology is C equivalent homology, just because T is a subgroup that is a deformation effect. B is T semi-direct N. Okay, in some direction, and N is a fine, so it's you can just send it to a point. Exponential. So this is convertible. B and C are homotopy equivalent. So this is nice. If you have B, you can just change it to T, and we kind of can do stuff with T. So this is nice. Any questions? Okay, so important property of G spaces that I don't think we will consider some other spaces. So like in this example, I told you that okay, we have this algebra of dimension n, and here we still have algebra of dimension n. And maybe another fact is there is natural map from X to homotopy inclusion, thus inclusion into first vector. It provides a map, pullback map from equivariant molecule of X to usual. And here in this example of CPM-1, it just sends all TIs to 0. So nothing remains. So yeah, send here the first coordinate and pull back, and it gives you this one. And I mean, it doesn't have to be surjective. If X is a group itself or something, then I mean, there are examples where this thing is very small. Or things we consider. What nice means in this context is as follows: to X is equivalently and if there exists H basis or this ring of a star G X that goes to a basis of which star X under one. So a free module such that its basis restricts my pullback to a basis of usual cohomology. And we will see how it can be proved. So I did not discuss equivariant fundamental classes, but they exist. So you write stratification of a space into G for T for torus, for T equivariant subvarieties, and the closures will give you bases both here and here. So that's something that we'll discuss on lecture 2 and 3, I guess. Borel-Moore homology and example for flag variety. Yeah, so like these spaces are nice and good. Yeah, so let me just tell you some other properties. So one operation on equivariant homology is pullback, but we also have pull forwards for certain maps, and we will only consider inclusions. So if G acts, so if Y is a G invariant space, then there are Gaussian maps, Gaussian pull forwards. So this is I pull forward from H star G Y to H star plus D G X, where D is sub manifold of X manifold. I hope. Yeah, manifold, submanifold of codimension D. In this case, we have a map that of degree D in the homology, which is, yes, so we will discuss the properties right now. The only properties I'll use is that push forward and then pull back is multiplication by top Chern class. Sorry, where did I put DG of normal bundle of Y in X. So it's a submanifold. We can consider normal bundle quotient of tangent bundles, and it's a bundle over Y and G equivariant, and we can consider its of rank D. We can consider its top equivariant Chern class. Yeah, any questions? Plus T. Yeah.
So say like a G invariant manifold, like let's say in this case, and then take like a equivariant vector bundle on it. And I have the equivariant Chern class. Is the way to retrieve like the normal Chern class, like forgetting the G equivariance?
I did not think about it, but I hope it. I mean, it's either obviously true or obviously false, and if it's obviously true, it follows from the definition of equivariant Chern class. I hope this is Cartesian. So you can like get a bundle over homotopy quotient, but then you can pull it back to get back this bundle So yeah, and since Chern classes are functorial, then this pullback, which is this map phi, will give you usual Chern class. I hope this proof is true. But if it's not, sorry. Yeah, of course. And yeah, so we just have to, yeah, let me just describe like two formal properties and one example. And I'll be finished in like hour and a half, as I planned.
Sorry.
Yeah.
But like, if you do something like, equivariant G, should go, and you should do expansion classes in star G.
Yeah, that's also true. Yeah. I don't know. I didn't think about that. I guess this proof is false. Yeah. Wait, wait. No, I don't think there are too many. Like I don't like if you. So the bad example here was like Ian, group and cell, but I don't think there are too many equivariant bundles in this case. Just vector space at one that you use group action to send each point. So I guess maybe so it's trivial. So I guess it has trivial chain classes as each group. Okay, well, this proof is rested. I guess. So where was I? I was here. Oh. Yeah, I can state the fact that trivial action gives equivariantly formal manifold, which is it's tensor product of usual cohomology and equivariant. So yeah, formal properties there is so let's say x y for equivariant formal. And let's say finite dimensional cohomology. I don't think we'll need anything else. Then we have equivariant unit. So H star Q x plus 1 is Gx, but C tensor product. So it's H star over this coefficient, over this ring that is everywhere, which is about G1. And there is also equivariant one correct Watson, which is a perfect pairing. Perfect. So H star G X tensor H star G point H star G X 2 star G point in the sense that it gives an isomorphism between H star G X and okay, I should have used the other for the string, but it's too right now. No, like dual, but over the string. So not only dual, but yeah, that's what I wrote. So I mean, it's a bit suspicious that there are no degrees here, but I guess it's yeah, I guess. it's just all homogeneous. There are no degrees. Degrees here. Yeah, so it's just formal properties that makes our life more convenient after we prove that these spaces are equivariantly formal. And maybe an example of such trick is the ring that we'll discuss on a third lecture. So H star G GB cross GB. So yeah, first there are like a bunch of tricks to, so we can, as I've erased here, we can eat with G to have H star B, just G over B, or we can send this B back equals B over G. Yeah, so yeah, what happens is yeah, so let me just write it. So like let's assume that this is equivariantly formal. So this is H star G over B tensor H star G point H star G over B. Then I get rid of this B, so just H star B point tensor H star G point over H star B point. And then I use that B is homotopy equivalent to T, so that I can change B to T. So this is S of T star tensor S of T star tensor over what? This is W invariance of T homology, so this is S T star W. Yeah, and it kind of makes sense. So this is so over this algebra. This is module of rank W because Chevallet-Bartov theorem, and it's kind of the number of cells. This is Brillouin decomposition. G decomposing that cells labeled by W. So yeah, we will discuss this example in more details in lecture 3. And yeah, this is everything I wanted to cover. Thank you for coming.